All right, we had a lot of trouble. Let me copy this link of the link for the stream and I mean this is becoming more and more annoying every single day. All right, if this works it's fine, otherwise we will see what we can do. All right. I hope the trouble was worth it. The ISP has seemed to find the seem to have found the perfect time for all of their works. Anyway, so as we were talking about, so we are going to, in this discussion we are going to talk about, we are going to rather continue our discussion that we last had in I think audio is fine, right? Again, YouTube is showing me a weird thing here saying you might not be able to hear the audio. So please let me know if the audio is fine. All right, let's get back to it. Let's just confirm the audio here. Okay, YouTube is somehow showing me that the current bitrate of current audio bitrate within brackets 0. Maybe I am streaming at 0 audio bitrate, right? Is higher than the recommended audio bitrate. Wow. So it is what it is showing, right? So now we in the last discussion we were talking about transient response of first and second order systems, right? Second order systems mostly. Okay. All right, and we did figure out the response of the systems. Okay, and for different conditions imposed on zeta, right? I discussed all these things, and I'm not going to explain those things once more, but in very brief, what we said. All right, so it is again showing me too many errors. I don't know what is happening. Anyway, so we said zeta was the factor responsible for damping the response, which means responsible for spending the energy in the system, right? Responsible for spending the energy in the system. And as such, for mechanical system, it was the viscous damper or frictional damper. Okay, anything that actually spends energy. By spends energy, I mean turns electrical energy or mechanical energy into heat, essentially unusable heat, for example, right? Something like that. Okay, so in a sense, unless you have a capacitor, unless you have a resistor in your circuit, what happens for a simple simple LC circuit? What happens in one cycle? The capacitor gets charged, okay, and on the next cycle the capacitor discharges by a current through the inductor, and that current once again charges the capacitor, and just like that the cycle keeps on going. So for an undamped system, the response is oscillatory and the frequency of oscillation is equal to omega n. So omega n is known as the undamped natural frequency. Okay, undamped natural frequency. And when zeta, now then the next condition was zeta had a sufficiently small value, like between 0 and 1, not equal to 0, not equal to 1, but between 0 and 1. And under this situation, we said the condition to be underdamped. So the damping has effects, but it is less prominent comparatively. Okay, so what happens? That we calculated everything, we did too much Laplace transform, inverse Laplace transform here, and we figured out that the response had a steady state part and had a transient part. Okay, the transient part was essentially a transition between two successive steady states. One was the off state, another was the on state when the system was on for a very long time. Okay, and this transient has a sinusoidal nature, but it is a decaying sinusoid because of this decay factor here. Okay, this e to the power minus sigma t actually helps the transient response decay. So essentially what happens, this oscillatory nature, even though it was there, it would eventually decay and it will eventually turn out to be 0. The oscillatory part eventually becomes 0, right? So now we essentially had shown that there are two factors which entirely would determine the response of the nature of the response of the system, right? So one of them was zeta. Zeta was the damping ratio. Okay, and this determines how fast the energy is lost, okay, or how fast the uh, transients would die down. Essentially zeta would determine how fast the transient would die down. If you look very carefully here, look at this equation. Okay, when we replaced all these terms, we had e to the power, look at the damping term here, e to the power minus zeta omega nt. So essentially having a higher value of zeta would mean that the damping would become faster, right? So the sinusoidal part would decay even faster. Okay, we're going to explain those terms, right? Now today's objective is to figure out these terms in terms of their particular values here, right? So of course, if the response kind of looks like this, then the response here takes a certain amount of time to reach the final value for the first time. This time is known as the rise time. Then it takes another amount, still a certain amount of time for it to reach its maximum possible response, right? This is called the peak response here. Okay, so the time it takes for the system to reach its peak response is known as the peak time. Okay, and while the peak response is happening, the amount of amplitude here by which the response overshoots, the peak overshoots the final value of the response, which is 1 here in this particular scenario, is known as the peak overshoot. Okay, by the amount by which the peak response overshoots the final response here. Okay, and then after a certain amount of time, we say the response has settled down. Once it reaches a 5% or a 2% band around the final value of the response and never leaves that bound. Okay, when something like that happens, we say that the system has settled down. Okay, and the time it takes to settle down is called the settling time. So we explained these terms here, and I believe we are going to start from that. So that was the small recap here. All right. All right. So someone, if you want to ask some questions, please feel free to ask. Okay. Let me launch that thing. If you have any query, feel free to ask. Just one minute, because I restarted my computer. All right. So this was the thing that I actually was talking about, right? So you actually have seen that in this application here in the last class, and we are going to explain this one. and we're going to explore more about the response of the system. Okay, so one moment please. All right. What is happening with me? Someone is not even taking a screenshot. Wow. Hold on. Weird. Hold on for a second. Okay. All right. Okay. YouTube is still complaining about audio. All right. So this was the thing, right? So now let's first calculate the rise time. So TR, the time it takes for the system to reach the final value of the response for the first time, right? All right. So let's copy this. Okay. We had this as the response of the system, right? So let's take this. All right. So this was the response of the system. So we want to figure out the time it takes for the system to reach the final value of the response for the first time. So question, what is the final value of the response? It was 1, right? Essentially because the transfer function we chose, okay, did not have this k here, right? So look very carefully, the transfer function we chose did not have a k or whatever here, right? So if I multiply this with 2 here, okay, the final value of the response would be 2, right? If I have k or p something like that here, the final value of the response will be that thing. So we particularly chose 1 here because we can just scale everything up, do an amplitude scaling, and things will work just as fine, right? So with that said, let's take that. And what is the final value of the response? The final value of the response is 1, right? So what we are looking for, essentially, we are looking for the time it takes for the system to reach the final value of the response for the first time, right? So essentially we are trying to figure out, essentially, say, so let me just again see what I am trying to figure out here. So we are calculating the rise time. Okay, so this is the rise time, right? This is the rise time. All right. Okay, so when time reaches the rise time, the response of the system would be equal to 1, right? because that is the final value of the response, right? So instead of this, if I say, so with that equation, if I replace t with tr, then that will be equal to 1, right? So we already have an expression for yt. What if I take that, bring it here, and instead say, okay, if I replace t with tr, so that's the rise time, right? Then it essentially becomes equal to 1, right? So we just replace the left hand side of the equation with this, right? So we already had an expression for yt. So instead of t, we're writing tr. So that's the rise time. So when the time reaches the rise time, the response becomes equal to 1 here, right? Now let's try to solve this equation. Of course, 1 will cancel out from both the sides. Now from this, I would have, so essentially after this line, 1 would cancel out from both sides. So I would have essentially omega n by omega d e to the power minus sigma tr, and then I would have sine omega d er plus beta. That's equal to 0, right? And of course, since these quantities omega n, omega d, these are not zeros or infinity or anything like that, I can cancel them out, right? Because we are equating to 0. And I can also, let me just say, so I can cancel these terms out, right? Because none of them are 0. So omega n is not 0, omega d is not infinity, so I can cancel them out. Now what about this term, e to the power minus sigma tr? That can never be equal to 0, right? That can never be equal to 0 because that's a decaying term by itself, and this can when tr is, if tr is somehow infinity, then only it can become 0, but that also as a limiting case, right? So this cannot be equal to 0, this can never be equal to 0, right? Similarly, this can never be equal to 0. So these two terms will cancel out. So this is the only thing that can become equal to 0, right? So we are equating a function to 0, then and it has 3 possible scenarios. Omega n could be 0, but it cannot. Omega d could be infinity, but still it cannot. Once again, e to the power minus sigma tr. Okay, it can only at a limiting case it can become 0, but we are not considering limiting cases here. And so this is the term this is the only term that can become equal to 0, right? So with that said, I have sine omega d tr plus beta to be equal to 0, right? We only have this scenario here, right? So that is equal to 0, right? Now, of course, with that said, what is the answer here? So would I write omega d tr plus beta equal to 0? Because sine 0 is 0, right? Sine 0 is 0. Would I write that? Of course, answer is no. So we are looking for general solution of trigonometric equations. You recall that if sine theta is 0, then the solution is theta is equal to n pi, okay, where n is a member of this set Zallen. So it could be positive, negative, and 0, all possible integers, okay. So essentially the solution is like the solution is like 0, pi, 2 pi, 3 pi, so on, minus pi, minus 3 pi, minus 2 pi, minus 3 pi, and so on, right? So any multiple of pi, whatever multiple, even 0 multiple of pi, that would do. So instead of writing 0, of course the solution is n pi. Got it? A very simple thing to understand, right? I think. Okay, where n belongs to this Zallen, right? Zallen is the set of integers, all positive, negative integers, including 0. Okay, so that's the solution. Let me write it down. So I'm saying then, of course, if I simplify this, on the left hand side I would have omega d tr plus let us bring the beta to the right hand side. So I would have n pi minus beta. All right. So tr is equal to n pi minus beta by omega d, right? All right, fine. Now try to understand one very important thing. N cannot be since beta is a positive quantity here, okay, since beta is a positive quantity here, and why is beta positive quantity? You people know that because beta, I think we defined beta, right? Of course, we did define beta, and beta was this angle, right? And let me say, yeah, beta was this quantity, tan inverse, okay, omega d by sigma. Now, omega d was a positive quantity, sigma is also a positive quantity. Since both of them are positive quantities, okay, since both of them are positive quantities, beta is a positive quantity, right? So, since beta is a positive quantity, so here beta is tan inverse omega d by sigma. Okay, since omega d and sigma both are positive quantities, this beta is also a positive quantity. Now if n is 0, then this entire thing becomes negative, time becomes negative, cannot be allowed, right? All right, if n is negative, then entire thing becomes negative, again time becomes negative, cannot be allowed, because we are only talking about causal systems, right? So that cannot be allowed. So here in our particular scenario, n can be equal to 1, 2, 3, 4, things like that, positive integers only, okay, not including 0, right? So we essentially have this kind of solutions. We possibly have solutions that would look like this: pi minus beta by omega d. This is one possible time at which the response reaches a value of 1. Then it could be 2 pi minus beta by omega d. That's also another time at which the response reaches equal to 1. So these are all valid answers, right? So 3 pi minus beta divided by omega d, and so on. Now why am I having so many answers? Because but the answer should be the answer should be unique, right? There should be just one answer, because look at this one again, look at this. So we have many possible answers, right? Pi minus beta by omega d, 2 pi minus beta by omega d, 3 pi minus beta by omega d. Okay, but if you look at this one, we only have one point at which it reaches this for the first time. But why am I getting so many answers? This can be answered very easily. Look at the graph properly. What are we trying to find out? We are trying to we are essentially equating the response to 1. So we are finding the solution, okay, for those times at which the response becomes equal to 1. And that is exactly why we are getting multiple answers here, because there are multiple points at which the response becomes equal to 1. Look very carefully. Okay, this is for the first time. Okay, this is that red dot. Look at this one. This is for the first time that the response becomes equal to 1. But then again, after some amount of time, the response once again becomes equal to 1, right? Look at this point. Then after a few more seconds, the response once again becomes equal to 1, right? And such. So this one in particular, this is the rise time we have been looking for, and that will be the first one. That will be the pi minus beta by omega d. Okay, so this will be the second one at which the response once again becomes equal to 1. So that will be 2 pi minus beta by omega d. This is the third time for which the response once again becomes equal to 1. So that would be 3 pi minus beta by omega d. All right, and so on. So it will again become 0 at certain point. Again, this keeps on happening, right? So the time we are looking for, actually known as the rise time, okay, would be this one, pi minus beta by omega d. So this is the first time for which this happens, right? All right, I think you got this, right? So with that explanation, therefore the rise time, therefore TR, which is the rise time, equals pi minus beta by omega d, discarding all the rest of the answers because they represent similar things, but after the first time, right? So this is the second time the system reaches a value of 1, the response reaches a value of 1. This is the third time the response reaches a value of 1, and so on, right? This keeps on happening. All right, so I think you get the answer here, right? Now if I just if I just simplify this even further, so pi minus, what was beta? Beta was tan inverse omega d by sigma and divided by omega d, and let's put the values, right? their particular expression. So tan inverse, right? So of course we would be given zeta and omega n, not omega d and sigma. So let's replace everything. So omega d is 1 minus zeta square omega n, and and sigma is zeta omega n, and omega d is again once again 1 minus root over zeta square omega n, right? So, and of course omega n here will cancel out. So this equals let's delete this. Let's bring it to the other side. So that's essentially pi minus tan inverse root over 1 minus zeta square divided by zeta divided by 1 minus zeta square. But I personally believe that remembering this formula is much easier than remembering this one, right? But just one thing in that you have to keep one very important thing in mind is that whenever you are using your calculator to calculate this tan inverse, make sure that the answer turns out to be in radians. Sometimes what happens, people do calculate this but their calculator somehow remains in degree mode. So essentially the answer they get in terms of degrees. So, and if you subtract a degree value here like that, okay, what happens, you essentially end up with a negative answer. So essentially what happens, many people calculate the rise time in negatives. They don't even think about it, that rise time cannot be negative, right? So this should be in radian. Okay, that keep that in mind. I think it should be a trivial discussion, but yeah. So keep that in mind. So rise time has this definition, right? So we have figured out rise time, and we are going to solve a particular problem with all these things. Okay, particular example. We will see how these things actually properly tally with this. Okay, so I think there is no issue with this. And if you find anything difficult to understand, feel free to ask. All right. So now next point. Okay, we are now trying to figure out the time it takes for the system to reach its peak response. Okay, so this is the peak, right? This is the peak response. So essentially this is the peak response. So again, this is the peak overshoot here, and the time it takes to reach the peak response is known as the peak time, right? So we are calculating now the peak time. So we are looking for PP, which is the peak time. All right, the time it takes for the system to reach its peak response, right? Now how am I going to calculate the peak response? Of course, by employing something you studied in your 12th standard, right? So what was that? Maxima and minima of functions, right? So of course that's a maxima of local maxima of the function, right? So this point, if you look at it, so and for the time, this is the time response, right? And that's this black one is essentially yt, right? This black one is essentially this yt, right? That's a yt function, right? And essentially look very carefully that this is essentially a local maxima, right? A local maxima of the signal or the function, right? So if I differentiate yt and equate it to 0, then the value would be 0 at this point, and then that would show me the local maxima and the local minima, all these points here, right? So essentially the idea is that the derivative of the signal or the function should be 0 at local extremas, right? So of course the point being that when is the maxima or a minima reached? For example, here the function was increasing, right? And here the function is decreasing. Okay, the point at which the transition happens, okay, from an increasing function it becomes a decreasing function. Okay, that transition essentially denotes a maxima. Okay, and And the other thing, if the from a decreasing function it becomes a increasing function once again, then that denotes a local minima, right? And at a local maxima or local minima, the derivative of the function must be 0, because the slope of the function at that point is flat, right? The slope of the function at that point is 0, right? Essentially, if you think about this line, okay, if you think about this line, so that is a tangent to the curve, right? So that's a tangent to the curve, right? So essentially the slope of that function would be 0 at that point. So when t is equal to tp, the derivative of the signal or derivative of the time response becomes 0. So how would I calculate this thing? By making sure that we employ the fact that the derivative of the function at the peak time is 0, right? So we're going to use that. Of course, in order to figure out whether it's the maxima or the minimas, we have to do a second derivative, but we are going to tactfully avoid that. We're going to see how we are going to avoid that and things like that. Okay, so we are going to keep that in mind, right? So let's differentiate the response, right? So let's bring the response once again here. Okay, the response is this one. Okay, let's differentiate this with respect to time. So y dash t. So if I differentiate this, of course this 1 becomes 0. Then I have minus omega n omega d. Now I have two things, two functions of time multiplied. So I have this function and this function, right? I have these two things multiplied. So I have to use the product rule of differentiation, right? I have to use the product rule of differentiation. So I have to first, I will first differentiate this one, keep this one constant, and then keep this one constant, differentiate this one. Let's write it down. So this becomes minus sigma e to the power minus sigma t Okay, someone is asking. Okay, someone is asking a very important question here. Question is, someone is asking. I mean, moments ago I talked about this rise time, right? So the point was the response reaches the value of one multiple times. Okay, and the interval it takes is equal. Okay, so this gap between two successive time instance where the response reaches equal to 1 is the same, right? So the gap between this and the gap between this is the same, and you can just verify that by making sure that you understand that pi minus beta omega d, 2 pi minus beta by omega d, 3 pi minus beta by omega d, these are in arithmetic progression. Okay, so they essentially have the same gap between them. Okay, so essentially after the same amount of gap, the response will once again become equal to 1. Okay, all right. All right, I think you understand that, right? And of course, what is this gap here? I mean, gap between two successive time instances where the response becomes equal to 1. What is the gap between that? You can just simply calculate that. That will be pi by omega d, right? So there is a time difference between of pi by omega d, pi by omega d. And again, what is pi by omega d? What is omega d? Omega d is the damped natural frequency. Then what is pi by omega d? Okay, that will be like half of the time corresponding time constant, corresponding time period, right? Okay, so these would essentially be those time instances where the sinusoid becomes 0. So these essentially, those are the instances where the sinusoid actually becomes 0, right? So that is what we did. We calculated the time instances at which the sinusoidal part becomes 0. Okay, and since this is a periodic function, okay, this will become 0 periodically, right? So within equal time intervals, it will actually become equal to 0. I think I answered your question, right? So let's go back to the derivative here. Okay, what about this signal? Look very carefully. I'm saying that this signal periodically becomes 0, and the points at which this part becomes 0, the response of the system becomes equal to 1, and that is obvious, right? If this part becomes 0, then the response becomes equal to 1, right? Now, of course, this is a periodic signal, right? It's a periodic signal, sine wave, right? So it will become 0 periodically. What is the frequency of this signal? That's omega d, right? Then what is the time period of the signal? That's 2 pi by omega d, right? Then what is the half of the time period of the signal? That's pi by omega d. And at every half interval, essentially the sine wave becomes 0, right? That's precisely the point here. Because a sine wave kind of looks like this, and at every half interval, essentially the signal becomes 0. All right, so we have this, and let's write it down. We have sine omega d t plus beta, and let's keep this now. And of course, we would have omega d outside, and that would be a cosine omega d t plus beta. All right, I think we did not make any mistake in calculations. All right. Okay, just one more thing. Okay, fine. Yeah, sure. All right. So that's the whole thing, right? But we know that, but this derivative, when time is equal to the peak time, this derivative must be equal to 0, right? So essentially, if I write this down and replace t with tp, this has to become 0. When it reaches peak time, the response has to become 0, right? Of course, this part cannot be equal to 0 because that's a constant part, okay, and that's a non-zero constant part, right? That part cannot be 0. So this entire internal thing must become equal to 0, right? So let's write it down. So we would have minus sigma e to the power minus sigma tp. Then we would have sine omega d tp plus beta plus e to the power minus sigma tp omega d cosine omega d tp plus beta, and that should be equal to 0. All right, so just keep following this properly. Okay, now of course, out of this entire thing I can factor out e to the power minus sigma tp, right? So if I factor out e to the power minus sigma tp, so I would be left with minus sigma sine omega d tp plus beta plus omega d cosine omega d tp plus beta, right? Again, just as the previous discussion went, this cannot be equal to 0, right? Because this can only become at a limiting case equal to 0 if the term here is infinity, right? So this cannot be equal to 0. So as long as I am finding out, I am equating it to 0, this part can be equal to 0, this sinusoidal related part, right? So I have minus sigma sine omega d tp plus beta plus omega d cosine omega d tp plus beta equal to 0, right? Right, we have that. So I think there is no confusion here, right? So let's bring this to the right hand side, cancel out the minus signs. So I would have sigma sine omega d tp plus beta equal to omega d cosine omega d tp plus beta, right? So we brought this part to the right hand side, cancelled out the minus sign. That is how we solve equations, right? Now bring this cosine on the denominator of the sine. So let's do a division here. So I would have sine omega d tp plus beta whole divided by cosine omega d tp plus beta, and that would be omega d by sigma. Someone is saying omega n and omega d. Why did you get omega n and omega d? Did I make any mistake anywhere? Please clarify your question. Someone is asking something. I cannot understand your question right now somehow. All right, but I think I'm doing it correctly. Okay, all right. So again, no, I don't get your question. So this is tan omega dt plus beta. That would be omega d by sigma. All right, no problem. But if you recall, let's go back to a much earlier class. What was tan beta? What was tan beta? Tan beta was omega d by sigma. Omega n divided by omega d from both sides will get cancelled. Did it get cancelled? I mean, is there any mistake in the solution that I did? Okay, look very carefully here. What was tan beta? Tan beta was omega d by sigma, right? Tan beta was omega d by sigma. So, by the very definition of beta, tan beta is omega d by sigma. So, this equation looks like tan omega dt plus beta, and this is tan beta, right? Since we know tan beta is omega d by sigma. Got it? Now of course, now we again have to look for the general solution of trigonometric equations, right? So let me say we have an equation that kind of looks like this: tan theta equal to tan phi, right? So you can just say theta equal to phi, but that won't be just doing justice to this, because you people know that there possibly are other values for which this equation still holds. Of course, this would hold true if theta is equal to phi, but that cannot be the case here, right? Look very carefully. If I just blindly write omega d t plus beta is equal to beta, it is just like writing theta equal to phi, right? In that case, the solution becomes t equal to 0, right? Did I just write t? Write down tp, huh? It's tp. So if I just write omega d tp plus beta equal to beta, then of course the beta will cancel out, the solution would be tp equal to 0. That does not make any sense, right? tp won't be equal to 0, we already know that. All right, so of course, then what is the answer here? Yeah, I did write omega d tp plus beta equal to beta. Then if I solve this, unfortunately the answer would be tp equal to 0, right? Beta will cancel out, omega d tp equal to 0 and tp equal to 0. But this is a wrong answer, right? I don't want that. Of course, who wants a wrong answer, right? So that's wrong, right? This cannot be solved this way. Okay, so now let's look at this one. Okay, let's see how we can actually figure this out. So we know tan theta is tan theta. Wow, fantastic thing. Okay, what if I write tan theta plus, say, pi plus pi? That also is tan theta. Okay, similarly tan theta, tan theta minus pi, that's equal to tan theta. Okay, same thing, right? So we are going to use that, and again we are going to consider the negative situation, we're going to consider the positive situation, because if we took negative, if we consider the negative situation, the value will once again become, the time will once again become negative. So for our situation here, I would only consider the positive multiples. So answer would be, essentially the solution here would be omega d tp plus beta is equal to beta plus n pi. essentially the answer would be this plus n pi. Okay. Got it? Okay. Again, n belongs to set of integers here, but I am going to consider only positive values here, right? I'm only going to consider positive values because otherwise the time becomes negative here. All right. So again, beta cancels out. So I would have Tp to be equal to n pi by omega t. Again, the point remains. Now we have multiple solutions once again, just like the previous one. So essentially I would have one solution as pi by omega d, one solution as 2 pi by omega d, one solution as 3 pi by omega d, but these will all denote maxima and minima. But how does that happen? How does that happen? Let me show you. All right, so we're looking for the maxima, right? So now look at this one. So this is a local maxima, right? This is a local maxima. Similarly, this is also a local minima. This point is a local minima, right? This is a local minima. Can you see that? Similarly, this is a local maxima, right? I don't think it is visible, the next one, but look at this one. This is a local maxima, but this is a local minima. Then this is a local maxima, right? So on and so forth. This keeps on happening, right? The response is oscillatory, so there will be always peaks, right? Just like that. Okay, so you can now understand that this is happening at the time instance pi by omega d. This must be happening at the next time instant for which the derivative is 0, which is 2 pi by omega d. This must be happening once again at 3 pi by omega d, because when time is pi by omega d, 2 pi by omega d, 3 pi by omega d, for all these possible values, the derivative of the response is 0, right? So they must all denote maxima or minima, right? Local maxima or local minima, right? So in that sense, pi by omega d is showing you the first maxima here, the first time this happens. Okay, and by our analysis we already know that the first time it becomes a peak, right? And okay, so it is the first overshoot here. Then at this point, this is the first undershoot, then it is the second overshoot, and so on and so forth. This keeps on happening. So this is what I'm looking for. This is what I'm looking for, right? So this is the first time for which this is happening, right? So this is essentially the peak overshoot. So peak overshoot. Similarly, this one is the first undershoot. Rather peak undershoot. So, right, again this is denoting the second overshoot, second peak overshoot, and so on. There is no question of harmonics here. Okay, someone is saying odd harmonics or something like, yeah, there is no question of those here. Okay, we are not applying Fourier transform here, and we are not going to talk about those. All right, so the peaks are happening at these instances. Again, these are again equally spaced apart, right? So again equally spaced. Again, the time interval through which it happens is pi by omega d, which is like the half of the time period for the sinusoid. So essentially we would have Tp, which is the peak time, that's equal to pi by omega d. If you just recall, just go back to the definition of the rise time, there it was just pi by beta divided by omega d. Okay, and it is just pi by omega d. Okay, and of course you can just write it down as pi by root over 1 minus zeta square omega n. You could write that, but I think remembering this way is a better idea. Okay, someone is saying yes, if it's an odd multiple here, then it becomes an overshoot, and if it's an even multiple, it becomes an undershoot. If you think about that, then it is. All right. I think there is no issue whatsoever with this. All right. So once we have calculated the peak overshoot, once we have calculated the peak time, our objective should be to calculate the peak overshoot. Okay, the amount by which the response overshoots the final value of the response, right? So let's calculate that. So we denote that with the term MP. Okay, so MP is essentially MP is essentially Y at peak time. So we are calculating the response at peak time. Okay, so what is the peak response? Subtracted from the final value, right? Final value, so which is Y infinity. So this is the steady state value. So this is the steady state response. And this is the peak response. By peak response, I mean the peak value of the response it reaches. All right, I think, right? So with that said, we have MP to be equal to Y TP minus 1. What is YTP? What is YTP? Look at this one. Let's go back. This is Y, right? Bring it here. So that's Y, right? Now that's Y. So I have to replace T with TP in order to get YTP. And then minus 1. This is that minus 1. Okay. So the minus 1 and plus 1 will cancel out. What? So this becomes minus omega n by omega d e to the power minus sigma TP sine omega d TP plus beta. All right. Now let's put the value of TP. Okay. So now, of course, we know the value of TP is pi by omega d, right? We just calculated it, the peak time, right? We did calculate the peak time. So that will be omega n by omega d e to the power minus sigma. So that will be pi by omega d, and then we have sine omega d into pi by omega d plus beta. Since TP is just pi by omega d, right? We have that. So now look at this one. So we have minus omega n by omega d and e to the power minus sigma. Okay, let me just write it down as sigma pi by omega d. Now we have sine. So this actually becomes pi plus beta. Okay, so this omega d will cancel out and this becomes pi by beta. Okay, but what is sine pi by beta? That's minus sine beta, right? So essentially this is omega n by omega d, okay, into e to the power minus sigma pi by omega d, and this is minus sine beta, so this minus sign will cancel out, and this will just become sine beta. Good. But what is sine beta? Let's go back. Okay, we defined it, right? What was sine beta? Sine beta was omega d by omega n, right? So let's come back here. So instead of writing sine beta, I would write omega d by omega n. So I have, of course, since sine beta is omega d by omega n. Got it? Now, of course, this omega d will cancel out and omega n will cancel out, right? I am just going to be left with e to the power minus sigma pi by omega d. That's it. So that's the amount by which the peak response overshoots the final value of the response, right? So that's your MP. Therefore, the peak overshoot MP is e to the power minus, yeah, just like that. Okay, just like that. Sometimes what happens, so just keep in mind, this is when the response has a value of 1, right? This is when the response has a value of 1. I'm going to shortly extend this for situations where the final value of the response is not equal to 1 but something else. Okay, but again, what is omega d and what is sigma? Let's just simplify this. This is going to be e to the power, and we have minus pi, and what is sigma? Sigma is of course zeta omega n, and divided by what is omega d? Omega d is 1 by zeta square omega n. So omega n will cancel out. Essentially I would have e to the power minus pi zeta divided by 1 minus zeta square. This entire thing is on top of e, right? So just keep in mind that the peak overshoot only depends, rather entirely depends on the damping ratio. Okay, it entirely depends on the damping ratio. It is completely independent of the undamped natural frequency. Okay, so let me show you what I mean with the demo here. Okay, see, here for example, this is the amount of overshoot we have. I just said that the amount of overshoot here, now you can notice the overshoot here. This kid is shouting once again. Again, look at this. Okay, this is given in terms, I have written this in terms of percentage, and I will shortly say why it is nice to write it in terms of percentage. But the thing is, it's a 30% overshoot. So for example, the final value is 1, then of course the overshoot is around 0.3, right? Around 0.3. But if I change the value of omega n, natural frequency, see, look at the response. Is the overshoot changing? I'm decreasing, increasing. See, I will leave it. We are looking at different values of omega. Notice here, but the peak overshoot is not changing. All the other features are changing, but the amount by which the peak response is different from the exceeds from the final value of the response is not changing. Look, see, right? So this is only dependent on the damping ratio. Now, of course, if I change the damping ratio, this peak will change, and as such, if I increase the damping ratio, the peak will decrease, right? If I increase the damping ratio, the peak will decrease, and if I decrease the damping ratio, the peak will increase. Now look at this one. When the damping ratio decreases, the peak increases, and when the damping ratio increases, the peak decreases. Okay, got it? All right, let's go back. All right, and the last one now is the settling time. So let's go back with the picture here. So we said settling time was the time it takes for the system to reach a bound of like 5% or 2% about the final value of the response, and then settle down there. So it won't be increasing beyond that. So when that happens, is that particular time is known as the settling time. We defined and we discussed all these things previously, right? Now, out of all these explanations, the definition for settling time is going to be an empirical explanation. What I mean is this. Again, let me just write it down. The settling time is denoted by TS. Okay. Now, of course, settling time is again an empirical definition by itself. By empirical means kind of not exact here, right? And again, the answer is not going to be exact here. Okay, the answer is not going to be exact. The point being, so look at the response. For example, let me just once again copy and paste, just as usual. Hold on. Okay, unfortunately, I have to go to the next page here. Nice. All right. So if you recall the response here, once again, let me just copy the response here. Where can I copy it from? Just copy. Right, this is the response, right? So ideally it takes infinite amount of time to reach the steady state. So I told you earlier that this is the transient, response, and this is the final response, right, or steady state response. Okay, so ideally it takes infinite amount of time to reach the steady state. So essentially what I mean is when time reaches infinity, okay, this part becomes zero, right? The transient part becomes zero. Okay, becomes zero when time reaches infinity. So when enough time has elapsed, the response becomes zero, right? That transient part becomes zero, but the steady state part remains, and then the steady state part is the only thing that remains. But of course, if you say it takes infinite time for the system to reach the steady state, it won't make any significant sense, right? because if you leave everything, if you leave any stable system for infinite amount of time, it will reach a steady state eventually, right? So that's not a technical discussion we can have, right? So but instead of saying the time it takes to reach the steady state, instead of saying that, we would instead say the time it takes for the system's response to settle down, right? So that is why this time is known as settling time. So we define settling time as a time that the system takes to reach about a 5% bound around the final value of the response. Okay, 5% bound about the final value of the response. Got it? So plus minus 5%. So yeah. So look at this one, this picture in particular. So we are saying that this is the settling time here. Because look at this one. So this is a plus 5% bound and this is the minus 5% bound. So this is plus 5% and this is minus 5%. Okay, got it? So, and this is the final value. Of course, the red line here denotes the final value of the response. So when, see, this is for the first time at this instance, this is for the first time the response goes into that bound but never goes beyond that. But look at this one. This is a point at which the response actually goes into that bound, but again it goes out of that bound shortly thereafter, right? So this cannot be considered the steady state. Okay, this cannot be considered the settling time. Okay, right? Here, but here when it reaches this point here at this time instance, it does not go back, it does not go out of this, right? It does not go out of this anymore. Okay, so the amount of time it takes to reach that particular bound and never go outside, and if the response doesn't go outside that particular bound, it's the time will be called the settling time, right? So with that said, now it is now it's time to discuss something called the envelope of the response. Now what is the envelope of the response? Now let me just draw the response. Okay, question is, how would I actually, if I didn't know better, how would I so if I'm given this, how would I draw this response? I mean, how would this one look like? How would this one look like if I ask you this? Okay, but in order to teach you that, let me teach you something slightly similar. Okay, all of you know how to draw sine theta or either sine t. If I ask you to draw sine t, all of you would be able to draw it. Okay, sine t looks like this. Nice. Bad plot, right? Let me just do this. Okay, so I'm asking you to draw sine t. Okay, and how would that look like? Let me just even do it a better way. Nice. Okay, so that's your sine t. Very simple, a simple sine wave. Fine. Nice. Okay, now what if I ask you to draw something like say t sine t? Okay, if you want to draw t sine t, how would that look like? How would that look like? Any idea? How would t sine t look like? Hmm? So instead of drawing this by hand, I think it would be better if I actually show you the drawing with a little bit of Python programming. Okay, it will be easier for you to understand. I believe strongly. Let me just open Python here. All right, so I have opened Spider. This is very handy for me at least. Okay, so I shall quickly draw a few things for you. Okay, just create a blank figure. All right. So now let's say I'm plotting this. So let me just say time is from -10 to 10. That would do. 1000 points would do. Okay, and let's say I want to plot t. Okay, again it is like okay, fine, that's your sine wave, right? No objections, right? Pure sine wave. Let me just draw a grid. All right, pure sine wave, no issues whatsoever, right? Now if I ask you, let me just do one more thing, because I don't think the time interval is fine, good enough here. Let's make this 15 and 15. That would be nice. Open a figure. Let's do a plot. Wait. Good. So we have a pure sine wave, right? So now if I ask you what is the plot for t sine t, I can use Python to actually plot that, but you will see what I mean. So if I say plot t comma t sine t, okay. This was on top of the sine plot, but look at this one again. Sine t. What another? All right. So this was your pure sine wave, right? This was your pure sine wave without any problem, right? Now, if I ask you to draw t sine t, how do you go about that? Okay, t sine t is essentially a product of t and sine t. So let me just draw t here. Okay, let's see. Okay, that's your t here, right? That's t, and on top of sine t, right? So again, since I'm drawing it on the same plot, it looks like this one, unfortunately. All right. So what if I draw t sine t? What happens? What happens is that this acts as an envelope. So if I do the plot here, plot t sine t. So let's plot t sine t. Along with that, let's plot t comma t and t comma y. Plot all these things. Now look carefully what happened. So this green, this blue one is t sine t, and how is that plot generated? That plot has been generated by multiplication of sine t with t. Okay, and this orange line representative of t. So that actually acts as something called an envelope. So envelope means that at this point the value of the response, the value of the signal or the function should have been 1, right? At this point, at this peak, right? But since this t is there multiplied with it, the value of this would be multiplied with t. So essentially this acts as an envelope, and that will be true for whatever type of envelopes I choose. So essentially when I multiply two signals like that, one of them acts as an envelope on top of the other. So let me just show you another example. Let me say, if I say, if I do plot the sine of 10t, maybe sine of t, and right. This is something known as amplitude modulation. So what happens, the green plot here actually representative of amplitude modulated sine wave. So essentially this is sine t into sine 10t, something like that. And how would you get that? Again, the overall here, this overall signal, okay, the envelopes are those low frequency sinusoids. Okay, and of course for envelopes we have reflections of the envelopes, right? So if we go back to our point here, okay, we so say so if this is the pure sinusoid, what is happening with my drawing? Somehow I cannot draw, unfortunately, today. Yeah, but the point being is that if I want to draw something like t sine t, what I will need to do, I would have to consider the envelopes. So essentially this is t equal to t, something like that, this equation. This is like y equal to t, okay, and this is y equal to minus t, and t sine t in that case would look like that. So you have seen a similar situation when you had drawn something like sine t by t. You are familiar with that, it's called the sinc function, right? So you have that. So this is like a multiplication of sine t with 1 by t. So what would 1 by t look like? 1 by t is a rectangular hyperbola. So this is what it looks like. Okay, and we also consider the negative of that. So minus of 1 by t. So this is minus 1 by t essentially. And so this is also minus 1 by t. And this one is 1 by t. This one is 1 by t. Okay. Again, with that, this function my drawing is really, really poor here. Yeah, for the negative values, why are you? So that is the convention of this. That is how this actually really works. Okay. Of course, on the negative values of y, we also have the same reflection, right? So for the negative values here, for example, when this signal actually reaches a value of -1, so here it had to reach a value of -1, right? It had to reach a value of -1, but it won't reach a value of -1 because that will get multiplied with the value of t, right? That will get multiplied with the value of t. So because of that, we write these envelopes here, but envelopes do not exist by nature, right? But we're just drawing that to denote that these values are bounded by plus minus of this function, right? These values are bounded by the plus minus of this multiplying function here. Okay, so when the values reach negative, this also will give you the negative values, right? So here the same thing will happen. The response would kind of look like this. So here we have a discontinuity, but this is going to be the sinc function. Yeah, something like that. Okay, so the envelope would be the rectangular hyperbolas. The reflections are essentially for preserving the negative values here, right? You get the point, right? So again, with this, what is the thing that we are multiplying with this entire thing, entire transient response? Okay, so what is the decaying factor responsible for the transient response? Is this one, right? Omega n by omega d into e to the power minus sigma t. All right, got it, right? So with that said, this is the response, right? And let's just copy this. Okay, so this is the portion of the envelope, right? That's that, right? So I'm saying that I'm looking for the time after which the response goes into a plus minus 5% bound beyond the 5% bound about the origin, about the final value of the response, and never goes beyond that. So if I say that, then I have to say that the transient response would have decayed and only 5% of that would be left, right? Only 5% of that would be left. Get the idea? Okay, so when time is equal to 0, okay, then what is the value here? What is the value of the envelope? So I'm saying envelope function. Here omega n by omega d into e to the power minus sigma t. Okay, so I am calling this function to be eta t. Okay, so when t is 0, okay, when t is 0, it is just going into the transient, right? It is just going into the transient. So what is the envelope function? So this is in full action in that case, right? There is no damping has occurred, whatever, right? And accordingly, when t is equal to 0, what is the value of the envelope function? Again, there should be a plus minus sign here, okay? So keep that in mind, but we can do it without the plus minus sign. Just look at this one properly. Okay, so that's the envelope function. And so when t is 0, then what happens? When t is 0, then this is equal to omega n by omega d. This is equal to omega n by omega d, because when t is equal to 0, that is what it is, right? Now we are trying to figure out a time into so let's try to put the plus minus. Be nice. Okay, so something like this. When the time reaches a certain value, which is known as the settling time, we are saying that this thing, so at that time we are saying that this thing will be about 5% of the original value, right? So this was the original value of the envelope, and we are saying when the time constant, when the time reaches the settling time, then it reaches a final value, then it reaches a 5% value of the whole thing, right? Of the original envelope value, right? So which essentially would mean that this part of the response, which is the transient part of the response, has become 5% of what it originally was, right? 5% of what it originally was, right? With that said, so that we're saying that this would be like 5% of epsilon 0, right? 5% of epsilon 0. We are kind of saying that, okay? So we are trying to figure out the time at which the transient response becomes 5% or less of the final response, of the steady state response. Got it? So initially the transient response was everything, then the transient response was decaying, and we're trying to figure out the time at which the transient response is only about 5% of the final response. So if I want to calculate that, then of course this is what it is. So at that point, so of course we have ETS, which is equal to omega n by omega d e to the power minus sigma Ts, okay, and that has to be, therefore that has to be e to the power minus sigma Ts, that has to be 5% or whatever percent. So we are saying 5% tolerance, 5% of E0. What is E0? That was omega n by omega d. Okay, we can consider the plus minus sign, you can get rid of the plus minus sign, doesn't matter. Okay, so 5% means 0.05, right? So 0.05, or less like that. So with that said, that becomes e to the power minus sigma Ts, that's equal to 0.05. All right, so now let's bring out our calculator and figure out what is the value of e to the power minus sigma Ts. Let's just say this is e to the power minus p equal to 0.05. Let's find out a value of p for which this happens. Okay, let's bring a calculator. Okay, we have a calculator in action. All right, so now let's say I have e to the power minus 1. Okay, e to the power minus 1 is like 0.36, won't work. So with that said, let's say e to the power minus 2, that's 0.13. Okay, that won't do. So let's say e to the power minus 3. Okay, what do I have? So e to the power minus 3 is 0.049. So if p is minus 3, then this condition has been satisfied, right? Because technically I don't want this to be equal to, I want it to be less than 5%. I want it to be less than 5%. I want it to be less than 5%, or rather equal, less than equal to 5%. Okay, so less than equal to 5%, something like that. Yes, absolutely. If I take a logarithm, this works perfectly. Okay, so instead of doing that, let's instead consider this to be the tolerance. So this is the tolerance, right? 5% is the tolerance. So something like that. E to the power minus p is the. So let me just generalize this. Okay, before we generalize, let's just put the value here. So p is turned out to be 3. Okay, keep that in mind. Okay, generalization. So if we consider what should I say? PS percent tolerance, PS tolerance, then again PS tolerance essentially means that if I'm considering 5% tolerance, then it's going to be 0.05 and such. Then e to the power minus p should be less than equal to 0. So it should be less than equal to PS. Now we are just writing it equal to because we are just approximating it. Okay, so essentially p would be equal to minus ln, p would be equal to minus ln ps. Okay, and what is p? P was sigma ts, right? P was sigma ts, so sigma ts, that's equal to minus ln ps. So what is TS? TS is minus ln PS by sigma. Okay. Now keep this in mind and consider the situation here. Consider the simple explanation here, right? So let me just explain. So if we choose a 5% tolerance band for defining TS, right? Then TS, so for this one, P is essentially again sigma TS, that's equal to 3. Then TS equal to 3 by sigma, right? TS is going to be 3 by sigma. Again, what is sigma? Sigma is zeta omega n. Okay. And okay, and there is another notation. So if we choose another notation, choose a 2% tolerance band, 2% tolerance band, then TS, if you just keep the same calculation, you will see, yeah, so 2.995, yeah, just that's approximately 3, right? And if you choose a 2% tolerance band, so if you consider this to be 0.02, okay, you will see that it turns out to be approximately 4. So that will be approximately 4 by sigma. Again, this is an empirical calculation. I'm saying this is not an exact calculation whatsoever. But whatever calculation I'm showing here, for settling time, this calculation is valid for small values of zeta. Okay. Remember, this is just an empirical calculation. Calculation valid for something like valid for 0 less than zeta less than 0.75. If you go beyond that, something like if you go somewhere beyond this, what happens? This empirical calculation essentially falls down. I mean, this does not work anymore. Right. Okay, this is just a rough calculation if you want to say. Okay, so time for solving a problem, right? Okay, so we are already seeing examples like this, right? So let's run this one. Okay, yes, tolerance band cannot be more than 5%. It could be 5%, it could be 2%. These are the two conventions we have. Okay, so let's take an example and we will end our discussion with that example, right? It's a very small example. So let's consider this situation where omega n is equal to 1 and zeta is equal to 0.35. Okay, so let's take this one. So we are considering a transfer function. So let's consider an example. So we are considering omega n equal to 1 for simplicity, unit is radian per second, and zeta is equal to 0.35. So our transfer function is gonna look like 1 divided by s square plus 0.7 s plus 1, right? Something like that. Of course, from this you can also figure out the value of, so this is 2 zeta omega n and this is omega n square, and you can calculate that. Okay, so now let's calculate the, so with this we have omega n. If I give you this transfer function, you can calculate omega n and zeta. So let's say instead of saying that, let's just say we gave you this, I gave you this. Okay, so of course omega n square turned out to be equal to 1. This is what it is. So omega n is 1 radian per second. Okay, so this 0.7 is 2 zeta omega n. So 2 zeta omega n is 0.7. So subsequently 2 zeta into 1, so omega n's value is 1, that's equal to 0.7, and of course zeta is equal to 0.35. Okay, all right. So now let's calculate the damped natural frequency. So again, whenever you're doing this kind of calculations, always calculate these things first. So this is going to be 1 minus zeta square omega n, right? So this is going to be 1 minus 0.35 whole square into 1. Okay, and let's calculate that using a nice calculator. So this is going to be 1 minus 0.35 square. Out of that, that's going to be 0.93, 0.94. This is going to be 0.94 radian per second. Okay, that is something we already have. Okay, and we are going to also calculate the value of sigma. Sigma is zeta omega n. Zeta omega n, of course, that's going to be 0.35 times 1, so that's going to be 0.35. All right, so we have all these values. So now let's calculate the rise time. So rise time is pi minus beta by omega d. So that's going to be pi minus beta, which is tan inverse omega d by sigma, okay, divided by omega d. Okay, so again, this is pi minus tan inverse omega d by sigma. I already know the value of omega d, that's 0.94, 0.94 by sigma. What is the value of sigma? Sigma is 0.35. This is going to be divided by 0.94. Okay, and now again let me show you this, the calculator part. So we are calculating, okay, tan inverse how do I calculate this? How do I calculate the inverse functions? Okay, tan inverse omega d by sigma, so that would be 0.94 divided 0.94. So now if you see, the answer is of course in degrees, right? Because I had degrees chosen. If you somehow do something like this, the answer is like 70 degrees, and pi minus 70 would be like a negative number, and dividing that by 0.94 would give you a negative answer, right? So don't do that. Always make sure to change these into radians, right? So if you do these calculations, always make sure to calculate these into radians. The answer is like 1.21, right? 1.21. So that's gonna be pi minus 1.21 divided by 0.94. So let's calculate this again. So pi minus 1.21 and divided by 0.94, that's going to be 2.05 seconds. Approximate calculation. How did you get 117.95? I think you did degrees, right? Make it turn it into radians. So 2.05 seconds, right? Look at the plot we had. Yeah, 2.06 seconds it's saying. Well, almost the same thing, right? So rise time is perfect for us. Calculated. Nice. Okay, everything is in radians. Don't make that mistake. Okay, so now let's calculate the peak time. Peak time is just pi by omega d. That would be the simplest thing, pi by 0.94, right? How much would that be? Pi by 0.94. That would be 3.34. That would be 3.34 second. Okay. What is the maximum overshoot? Peak overshoot. So that was e to the power minus, what was the expression? Yeah, e to the power minus sigma pi by omega d. To the power minus sigma pi by omega d. So that was e to the power minus sigma pi over omega d. So what is the value of sigma? Sigma is 0.35, and so that's going to be exponential minus 0.35 into pi and divided by omega d, that's 0.94. Okay, so that's going to be e to the power, that's going to be e to the power minus 0.35 times pi divided by 0.94. That's about 0.31, right? That's about 0.31. So again, this indicates that the peak response is higher by a value of 0.31 if the final value of the response is 1, right? So essentially we can represent this as a percentage. So we can say this is like 31% approximately, right? So this is like 31%. So if the final value of the response is something else instead of being 1, then this would still be 31%, right? So if the final value of the response is 10, then 31% of that. Okay, whatever is the final value of the response, that much percentage of that. So we often represent the peak overshoot with a percentage. And settling time. Settling time, so we are considering, say, for example, 5% settling time. If I consider the 5% notation, so that's going to be P by sigma. So that's going to be P by 0.35 here. That's going to be 8.57. All right. All right. Now you would see something very interesting here. All of my calculations would match with the actual results, right? Except for the settling time. The result I would calculate to the empirical calculation. This calculation will not match with the final with the thing that we programmatically calculated here. So this value has been calculated programmatically here. Okay, this is exactly when it settles down. Okay, but the calculation I am showing you to this is an approximate calculation. So this is not an exact answer, right? Not exact. So this result will possibly never match if you programmatically calculate it, right? So this is where I calculated it programmatically. Everything else matched. Peak time matched, maximum overshoot matched, all of these things matched because these are exact calculations. But settling time here, for this example, I did calculate this programmatically, right? So Python actually looked for the value of time at which the response actually went into that bound and never went beyond that. Okay, so the correct answer is 7.86 seconds, right? But the empirical result is something like this. So that is why it is empirical. Okay, this answer is never correct. This is more of an approximate solution. Just keep that in mind. So that will be the end of discussion here. So okay, your homework would be this one. Again, if you have any query, feel free to ask. So we have only considered underdamped systems so far. Okay, keep that in mind. All right, calculate all these things: omega d, omega n, omega n, zeta, omega d, final value of the response. Using final value theorem, you can just apply final value theorem to find the final value of the response. Okay, rise time, peak time, maximum overshoot in terms of percentage. Okay, and settling time, consider a 5% bound. Yeah. I won't ask you to calculate sigma, but you have to calculate sigma anyway. Okay, any query, feel free to ask. Otherwise, we're going to end the stream here. We had a lot of trouble today. Thank you for being here. I will see you tomorrow with our Python programming class. Just one more hint. You have to just keep in mind that, let me just say, instead of calling this 10, let's make this 100. It would be much better. Right. All right. So thank you very much. Let's end our discussion here, and I will see you tomorrow.